Hello there. I'm glad you're here. Maybe your day has been long, or maybe you simply prefer drifting off with the night sky for company. Either way, let your shoulders soften, your breath even out, and your thoughts grow lighter as the room gently dims. Tonight, we'll step beyond our warm sun, past the familiar paths of the planets, past the faint ring of icy worlds in the Kuiper Belt, toward the wide, quiet spaces where our small probes keep going. We'll wonder what lies outside the solar system, the far snow globe of the Oort Cloud, the thin breeze of interstellar space, the space between stars and the nearby suns that whisper across that dark sea. There's nothing to solve and nothing to hurry, just a calm walk among big ideas, taken at a sleepy pace. If this gentle journey brings you ease, a soft tap on like and subscribe helps other night travelers find their way here too. For now, close your eyes if you'd like. Feel the breath arrive and leave, and let the dark carry you. When you're ready, we'll begin. Step out with me, gently, as if we were easing onto a quiet porch at night. The air is soft. The world has put away its noise. Above us, the sky holds more stars than any story can carry, each one with its own weather of light, its own slow seasons, its own family of worlds. Astronomers keep listening with wide, careful instruments. Their surveys sweep the sky like brooms of patience, and new points of interest appear almost daily. Shy, variable stars, steady red embers, planets tugging at their suns and dimming them by a breath as they pass. Some are scorched and racing. Some are cold as winter glass. Even the untouched distances feel inhabited by possibility. And here we are, on our small, warm stone, with oceans and leaf shadows and coffee steam, lifting our gaze just enough to feel the roof of the universe like a calm hand over the brow. Closer than all the far fires, a single light keeps us. The sun, bright enough to paint a room through closed curtains, generous enough to make wind and rivers and harvests possible. We think of it as a disk, simple and steady, but it is a living engine with weather of its own loops and lashes of magnetism, sudden blooms of X-rays, breath that streams outward as a wind. To learn a star, you sometimes have to walk right up to the furnace door and listen to the roar, not with ears, but with instruments that can sip the heat without breaking. That is why a small, heat-armored traveler Parker solar probe was sent inward, falling like a patient spark toward the corona, the sun's pale flame crown. On a November night in 2021, Parker slipped close enough to taste that thin, electric atmosphere, the first craft to touch the corona. Imagine a place where light is everywhere, and yet the gas is so spread out you could pass through it like mist. Imagine space that glows not because it is crowded, but because it is excited, threaded by fields you cannot see, but that push and pull like tides. Parker's path brings it nearer in spirals, each loop tightened by the quiet theft of speed at Venus, a graceful borrowing of gravity that trades distance for knowledge. In time, its closest sweeps pass just a few million miles above the sun's visible edge, where heat could melt iron and the wind becomes less a breeze than a river of charged particles, swift and bright. Why venture there at all? Because our days are braided with the sun's moods. The solar wind, those quick, thin streams of protons and electrons, shapes a vast bubble around us called the heliosphere, a kind of weather system that stretches far beyond the last icy crumbs of the Kuiper Belt. Sudden flares can disturb radio, paint the poles with auroras, jostle satellites. Quieter changes set the rhythm of that wind and the structure of space itself. The closer we look, the more a puzzle glows. The surface that we see, the photosphere, is about as hot as a kiln, roughly 5,800 Kelvin. But above it, the air grows hotter again, first to tens of thousands in the chromosphere, then to millions in the corona. Heat, which we expect to leak away with distance, seems to reverse its flow. Somewhere between light and magnetism, energy is being smuggled upward. The sun is both ordinary and exceptional. It's a G-type main sequence star, about 4.6 billion years into a long, steady burn. By count of atoms, it is mostly hydrogen, with helium as its nearest companion. By mass, hydrogen still dominates, followed by a quarter share of helium, while everything else, carbon, oxygen, nitrogen, iron, and the rest, makes a small but important seasoning. At the very heart, the core pressure is so absolute and the temperature so keen on the order of 15 million Kelvin that hydrogen is coaxed into becoming helium. In that change, a fraction of mass vanishes into energy, and the equations of relativity speak themselves as light. The density there is a quiet astonishment. A single cubic meter would weigh as much as a small building. Photons, born in that brilliance, don't fly straight out into day. They ricochet and wander through the radiation zone for tens to hundreds of thousands of years, a long, foggy migration. Only higher up, in the convection zone, does the star begin to boil in great, slow cells, hot material rising, cooler material sinking, like the surface of water just before it sings. We see the top of that singing as granulation, grains and petals of brightness that change on the timescale of minutes. Along the limb, hairline jets called spicules leap upward by thousands of miles, vanish, and are replaced by new ones. During a total eclipse, the chromosphere reveals itself in a brief pink rim, and the corona arches outward in ghost white streamers. All of this rests on the architecture of magnetism, fields wound up by rotation and convection, twisted by time, broken and rejoined in bursts that fling energy outward. The sun's magnetism is no simple bar. It is a braid that reweaves itself, flipping polarity every 11 years in a long breath we call the solar cycle. Spots come and go, flares strobe. The wind changes its temper. The question that tugs at the sleeve is gentle and stubborn. Where does the extra heat for the upper layers come from? And how is the wind pressed into such speed? One line of thought says that waves born lower down are fan waves. Ripples in magnetic tension carry energy upward and shatter into heat, like ocean surf breaking into spray. Another says that small, frequent reconnection events, tiny persistent nanoflares, spark so often that their sum is a warm rain. There are other possibilities involving turbulent cascades or the particular ways charged particles steal a ride on changing fields. The truth may be a chorus rather than a solo. Parker was built to listen to that chorus up close. Its white-faced heat shield is a thick carbon-carbon loaf, sunlit side blistering while the shadow stays almost room comfortable for the instruments crouched behind it. It carries sensors for fields and for particles, a wide field camera that can watch the solar wind itself as a textured flow, and detectors that can feel the shape of waves in the plasma. On each close swing, it tastes the chemistry of the wind, counts the particles' energies and directions, and trims its data down to what matters most, so the signals can thread back through the noise of the sun to the dishes on Earth. There is something tender about that. A small craft, cooked on one side and kept cool on the other, reading the weather of a star, then whispering home between bursts of interference. Speed comes with falling. Near its tightest passes, Parker moves faster than anything else we've made, well over 100 miles per second, quick enough that the stars seem to creep while the sun swells and recedes. At times, the shield glows with heat intense as a forge, temperatures higher than any planet's noon. The orbit is shaped so it can sprint past danger and then breathe out its heat in a longer, safer arc before turning inward again. Each rendezvous with Venus steals just a little more of its grand momentum around the sun and folds the ellipse tighter. From pass to pass, the path becomes less like an oval and more like a hand laid gently on the fire. Meanwhile, back at our quiet porch, we remember scale. The sun's diameter is more than 100 Earths end to end. By mass, it gathers almost everything in the solar system into itself. And yet among the city of stars, our kind or brighter are not the majority. Most stars are smaller, cooler, and dimmer red embers rather than yellow flames. Our star is ordinary enough to teach us about many others, and idiosyncratic enough to be itself. Learning its habits helps us read the wider neighborhood. It tells us how winds fill the heliosphere, how shocks and storms travel, how space between planets is not empty, but alive with charged threads and echoes. As Parker keeps spiraling, it carries small, human hopes, not just the romance of touching a star, but the practical calm of understanding our space weather better, of making power grids sturdier and forecasts wiser, of treating satellites like ships that can steer with knowledge rather than drift on rumor. There is poetry in that pragmatism. To listen well is an act of care. To measure without hurry is another kind of reverence. Eventually, the little craft will tire. Electronics age quickly under radiation. Materials grow brittle with cycles of searing and shade. The orbit will change as planned and then hold, and one day the instruments will go silent. Whether it lasts years longer than expected or keeps perfect time to its design, the ending will be simple. A light switched off, the path still there without the traveler. Some projections imagine the orbit decaying in the long future, letting the spacecraft finally fold into the star it studied. Even if the finish is less dramatic, quietly fixed in a near-sun loop, the feeling is the same. Parker's life is a small flame given to understand a larger one. Meanwhile, the data keeps arriving. Packets of field lines drawn in numbers, grains of wind sorted by energy, pictures of the faint dust and light around the sun that look, astonishingly, like weather seen through a cracked window. Scientists lay out those pieces on long tables of code and careful plots and find that the show has fewer blanks than before. They see waves where theory said waves should be. They see particles accelerated in ways that make mathematical sense. They see hints of those tiny, constant sparks that might, in their millions, explain how the upper air is kept so hot. Nothing is finished, but a fog has thinned. Lift your face a little and feel the warmth through the night's cool. A star 93 million miles away can still reach the skin with a memory of day. That same star drives winds that fill a bubble big enough to carry our spacecraft past Pluto and farther. a wind that once braided the tails of comets we watched from fields as children. When a small probe dives into that wind and finds patterns where we suspected only noise, it is not just a victory of engineering, it is a deepening of peace. The more we know the temper of our local star, the kinder the space around us seems, not because it is safer, but because it is legible. And legible things can be lived with, even loved, and that kindness extends inward to the small, tight orbit where a shy world keeps near the Sunday. Think of the evenings when the sky is still pale and the air is not yet night. Low over the horizon, a quick glint appears and then slips away, as if it prefers to be noticed only in passing. For a long time, people thought there were two of these glints, one in the morning, one in the evening, two different wanderers wearing the sun's light. It was the same world all along, revealed only when the glare loosened its hold. Mercury, the little messenger with a bright face and a quiet story. Telescopes had a hard time with a planet that hugs the sun so closely. Heat, haze, and daylight interfere, and yet patience has its own optics. Bit by bit, with instruments that can stare without blinking, the outlines of this world came into focus. Mercury is small, its radius about 2,440 kilometers, a little more than a third of Earth's. By mass, it's roughly 1/20th of Earth, and yet heavier than two larger-looking moons, Ganymede and Titan, put together. That density is a clue. Inside, a metallic heart takes up an outsized share of the body, an iron-nickel core around 2,000 kilometers across, more than half the planet's volume. Around it lies a comparatively thin silicate mantle, a few hundred kilometers thick, and over that, a hard, stony crust, not much thicker than a mountain range, is tall. The planet rotates so slowly that it barely bulges. Equator and pole differ by less than a kilometer, a roundness that feels almost ceremonial. How did a world end up so core and so little coat? Two families of ideas sit beside each other without quarreling. One says the early sun blasted the inner disk with heat and light, sweeping away lighter materials and leaving a metal-rich remnant close in. The other imagines a great scouring, a giant impact in the young system when planets were still reckless, that stripped away much of Mercury's outer rock. Either way, what remained is a compact ember with a liquid metal heart and a surface that keeps the record of ancient weather made of stone. That surface is old and lyrical with craters, the pocked handwriting of time. Much of it has lain quiet for billions of years, with the loudest sculpting happening early, when the solar system was still crowded with debris. There were later flows, though broad, dark plains where lavas once spread and cooled, and delicate features that look almost like frostwork carved into rock. Messenger, the spacecraft that orbited Mercury from 2011 to 2015, found bright, strange hollows, shallow depressions that seem to form when volatile materials in the crust escape, leaving scalloped rims that catch the light. It's an unexpected softness in a place of such extremes. Before that deep look, we had only half a map. In 1974 and 1975, Mariner 10 swung by 3 times, working at the limit of what cameras and star trackers could do, so close to the Sunday. It imaged about 45% of the planet, tasted the heat, and sensed a surprise. Mercury has a global magnetic field, faint but definite. Not a leftover magnetized rock, but a dynamo, like Earth's, although offset toward the north and much weaker. Around that field is a small but sturdy magnetosphere, a shield that meets the solar wind head-on and rings like a bell when buffeted. Between planet and space is not an atmosphere in the usual sense, but an exosphere, so thin that atoms seldom meet helium and sodium and oxygen, that leap from the surface, dance in sunlight, and trail away in a long, golden tail that telescopes can see from Earth on the right nights. Even without air to speak of, Mercury breathes. Messenger filled in the rest. Launched in 2004, it took a winding, thrifty path, borrowing speed from Earth and Venus before settling into orbit in 2011. Over 4 years, it returned hundreds of thousands of images and a deep stack of measurements, gravity maps that let scientists weigh the core more exactly, laser altimetry that traced every swell and hollow, chemical fingerprints that told which planes were volcanic and which were impact melt. It watched the exosphere thicken and thin with the sun's moods and tasted the way magnetic reconnection field lines, breaking and rejoining, can snap like dry twigs in a breeze. When its fuel was gone, it bowed into the surface and vanished in a small, quiet spark, leaving the planet more legible than before. Mercury's path around the sun is an ellipse pulled long close in at about 0.31 astronomical units, farthest at roughly 0.47, with a semi-major axis of 0.387. It completes that loop in 88 Earth days. Its rotation is caught in a 3-to-2 rhythm. With its orbit, the planet turns 3 times on its axis for every 2 trips around the Sunday. That dance means the same longitudes come under the sun, near perihelion. Again and again the hot longitudes, where noon can climb towards 700 Kelvin, metal soft heat. From the surface, the sky would tell time in slow, peculiar ways. One sunrise to the next takes about 176 Earth days, and near perihelion, the sun would seem to pause and even backtrack for a while before continuing, a mirage of motion born from resonance. On the day side, the ground bakes. In the long nights, without air to share the warmth, the temperature falls far below freezing swings that feel like lullaby verses read in ember and ice. And yet at the poles, a different story holds steady. Mercury's axis is tilted by only a hair, so some crater floors near the poles never see the sun, not for millions of years. Radar from Earth first saw bright patches there, and Messenger confirmed what the brightness meant. Water, ice, draped with a thin blanket of dark material, probably organics, that insulates the frozen layers beneath. In the near-permanent dark, temperatures sink toward 80 Kelvin, cold enough to store the simplest memory of comets and asteroids that once delivered these volatiles. A few ridgelines nearby catch constant light and can warm above 100 degrees Celsius, testing the border between shadow and shine. Close, but not mingling. Without air, heat does not travel far. Elsewhere, the planet wears its history openly. Caloris Planitia, the plane of heat, is a basin so wide you could set a continent inside it, about 1,550 kilometers across. It formed near the end of the heavy bombardment, something on the order of 100 kilometers wide, striking a young crust and ringing the world through. Shock waves focused on the opposite side of the planet from the impact created a jumbled, weird terrain there, a chaos of knobs and hills like frozen surf. Inside Caloris, lavas later welled up and paved much of the floor with smoother plains. Along the rim, faults and wrinkle ridges record the basin's slow settling, like a great dish flexing as it cools. Near the center of Caloris is a puzzle that looks almost deliberate from high above. Pantheon Fossae, a starburst of troughs, hundreds of them radiating from a focus like lines drawn with a compass. Their widths are on the scale of a town, their lengths on the scale of counties. At, or very near, the hub sits the crater Apollodorus, whose rays cut across some of the troughs. Whether it caused the pattern or simply took advantage of a faulted place to carve its circle is still a quiet debate. The troughs themselves are thought to be extension faults, places where the crust was pulled slightly apart as the basin relaxed, or as deep magma chambers emptied. The rock did not shatter all at once. It exhaled in spokes. Traveling across longitudes, another basin waits with a different mood. Rachmaninoff is smaller, about 290 kilometers wide, but its interior glows with a warmer color in Messenger's instruments, a sign of distinct composition. Inside the main rim lies a ring of peaks, the inner ring common to large impact basins, and within that ring, smooth plains show patterns of flow. The idea that these are volcanic and relatively young by Mercury standards makes the basin feel like a last note that lingered after the broader music of volcanism faded. Measurements place the floor well below the global mean, one of the planet's deepest spots, as though the impact and later activity both pressed the surface downward and kept it there. Between and around the big basins rise cliffs with names that sound like ships. The largest scarp known, Enterprise Rupes, runs more than 800 kilometers, a wall of broken crust that in places towers a few thousand meters high. Rups means cliff, but these are not cliffs from rivers or seas. They are faults born when Mercury cooled and, like an apple in a winter window, shrank a little. The crust had to tuck in the slack. Thrust faults shoved blocks of ground over other blocks, and the surface wrinkled into long, sweeping faces. Over the planet's lifetime, it may have lost several kilometers of radius, a small change for a globe, but a grand one for the skin that must adjust. Enterprise Rupes crosses into Rembrandt Basin, a 716-kilometer bowl with a complicated interior of ridges and fractures, the floor patterned like glass that is cooled unevenly. In Rembrandt and elsewhere, you can read the same script: contraction, impact, volcanism, all layered and interleaved. The magnetism is a character of its own. Mercury's field is only a few percent of Earth's strength at the surface and is shifted northward by a noticeable fraction of the planet's radius. That asymmetry makes the southern hemisphere's magnetic protection thinner and the northern thicker, a lopsided umbrella. Solar wind drapes and tears at it. Reconnection events flash on the day side and send particles raining along field lines to the surface, where they liberate atoms and feed the exosphere. Sodium glows along the terminator like dusk seen from space. Every flyby and every orbit adds notes to this score, and models grow gentler and more accurate in the way they mimic the planet's small storms. Even with so much learned, the world stays a little reticent. That's part of the piece here. Not everything has to be taken apart in one sitting. Another visitor is on its way, unhurried and precise. Bepi Colombo, two orbiters traveling together, one tuned to the surface and interior, the other to the magnetic bubble and charged particles, left Earth with a long itinerary of gravity assists. It has already skimmed Mercury more than once, taking snapshots as it bends its path into something the planet can catch. When the pair finally separate into their own orbits, They will map composition in fine detail, watch the exosphere breathe day by day, and listen to the dynamo inside by tracing wrinkles in gravity and subtle tugs in motion. The aim is simple: kindness through clarity. Better stories about how a small world cools. Better estimates of how often fields snap and reconnect. Better portraits of ice in shadow and lava in light. Meanwhile, Mercury keeps to its rhythm, a 3-2 drumbeat under the sun's steady blaze. In the morning and evening, it shows itself to patient eyes, and in between it does what worlds do: turns sunlight into slow geology, trades heat with night, carries a past in its scars and a present in its whisper-thin breath. From a distance, it can look like a bead on a wire, almost an afterthought. Up close, it is a complete place with its own weather of particles, its own archives of fire and frost, its own way of standing inside the solar wind like a stone in a river. The legibility we've won here doesn't tame it. It lets us stand nearer without strain. A small planet becomes a familiar neighbor. The glare softens, and what we see can be lived with, even loved the same kindness we felt in the wind of the sun, to a world that hides in plain sight. Venus moves through the evening like a lantern veiled in silk, low over rooftops and tree lines, bright enough to cast a faint shadow if you let your eyes adjust. It is close enough to visit with a tilt of the chin, and yet difficult to read, because its face is always turned to us in cloud. The orbit keeps an easy pace, about 225 Earth days for a full loop at roughly 72 hundredths of the Earth-Sun distance, and every 584 days or so, the geometry between our two worlds lines up, and the distance narrows to about a quarter of an astronomical unit. By a near coincidence of rhythms, the same hemisphere of Venus tends to face Earth at these encounters, as though a dancer were choosing the same pose at each bow. Whether tides have gently nudged it that way, or whether timing itself is the culprit, remains an open, courteous question. Set next to Earth, Venus feels like a sibling. The size is nearly the same, an average radius near 6,052 kilometers, about 95% of Earth's, and the mass is about 82%. But the family resemblance fades when you watch how it turns. The planet spins backward, a slow retrograde rotation taking roughly 243 Earth days to complete, so slow that its day is longer than its year. Relative to its own orbit, the axis is nearly flipped, a backwards top barely tilted. From the top of the clouds, the sun would drift west to east, lazy and pale behind curtains of acid haze. And beneath those curtains lies a story that once invited daydreams of jungles and seas, then replaced them with a truth far stranger and more instructive. The first clear maps had to be made without light. Radio waves slip through the clouds and return whispers from the ground. Radar tells shape by timing and texture. Pioneer Venus began the work in the late 1970 seconds, and the old Soviet Venera orbiters helped. Then, in the 1990 seconds, Magellan took the method to its patient limit and stitched together a portrait of the surface with a resolution fine enough to show individual flows and ridgelines over 95% of the globe. The result is not a twin of Earth, but a distinct geology, written in basalt and pressure and heat. Inside, the structure is familiar: an outline, metallic core, silicate mantle, crust, but the behavior is its own. A significant core, perhaps a quarter of the planet's mass, is likely at least partly solid today. There is no global magnetic field to speak of, only an induced one when the solar wind presses. The silicate mantle reaches down thousands of kilometers, topped by a crust on the order of tens of kilometers thick. Yet the crust does not ride in mobile plates, as ours does. The heat and the viscosity of the rocks make for a shell that deforms in broad sweeps rather than in rafts. Stresses gather and are released differently, and the landscapes that rise from that difference look like nothing else we have. Much of the surface is a dark ocean of basaltic plains, frozen lava that drowned older terrain. Across and within those plains stand features with names that feel almost mythical, but are exact in their meaning. Tesserae tiles are high, rugged provinces, crisscrossed by intersecting ridges and troughs, folded and refolded, as if the crust had been pressed from many angles at once. Coronae are great, circular or oval crowns, some hundreds of kilometers across, where upwelling from below may have domed the surface, and then let it sag and crack in concentric and radial patterns. Arachnoids, more delicate and rarer, weave rings and spokes like spiderwork in stone. To an unpracticed eye, the radar images can look uniform, but elevation maps, painted in careful color, reveal continents and basins in relief, and the planet's personality comes forward. Aphrodite Terra sprawls like a long, ragged continent near the equator, some 18,000 kilometers from end to end, and around 5,000 across, in places an area that could be compared with Asia. Its pieces wear the names Alpha, Beta, and Gamma Regio, and each has its own tempo. In the east, Alpha Regio rises and falls with tangled ridges. Nearby and elsewhere in Aphrodite stand broad volcanic constructs whose heights, measured from the surrounding plains, run to several kilometers. Their flanks are laced with channels and collapsed pits, and the absence of impact craters on some flows hints that parts of this story are relatively young in geologic time. In the west, a different mood takes over at Beta Regio, a bright, round swell, some 2,500 kilometers across, where deep fractures cut the ground and long, smooth lavas have poured from fissures. The pattern of forces here, extension in one set of directions, compression in another, reads like the aftermath of repeated stirring from below. South and west of these rises, the ground relaxes into Guinevere Planitia, a lowland wide enough to hold countries. Plain sounds flat, but even here, the crust is not featureless. Wrinkle ridges and lava sheets layer over one another, and the margins knot into modest uplands. Somewhere in this general sweep of latitudes and longitudes, robust metal capsules from the Venera program came bruising through the atmosphere in the 1,970 seconds and early 1,980 seconds, and made the first photographs from the surface cobbles and slabs under a sepia sky, and the first measurements of chemistry that matched basaltic rocks on Earth. Each lander lived for less than a spell of an hour or so, long enough to send back the taste of a world that remakes the word hot. Far to the north, the terrain gathers itself into a second great highland, Ishtar Terra, with a breadth east to west of about 8,000 kilometers. Along its eastern edge, the ground climbs into Maxwell Montes, Venus's highest massif, 11 kilometers above the planet's average radius, about 7 above the surrounding plateau. Up there, an air still crushing by our standards, yet a little thinner than at the lowlands. Temperatures are fractionally cooler, still on the order of 380 degrees Celsius, and the radar brightness increases. One way to read that brightness is as the sheen of metallic compounds that have evaporated from low, hot plains and condensed on the coldest high slopes, a kind of glittering snow of sulfides that reform and sublimate with altitude. It's a vision of mountain weather in a place where cold is an ironical word. The catalog of shapes continues like a book of etchings. Fractures radiate from coronae like the ribs of fans. Long sinuous channels, some carving for thousands of kilometers, meander through plains as if cut by water, though they are too hot for liquid water, and are instead the paths of extremely low viscosity lavas that once streamed and cooled. Pancake domes sit quietly, steep-sided and almost symmetrical, as if lifted from a griddle, and everywhere the count of large, fresh impact craters is unusually low for a world this battered by time, suggesting that at some moment in the geologically recent past, the surface was resurfaced on a grand scale by volcanism or by a surge of tectonic overturn. The planet may reset its skin, not piecemeal, but in broad, infrequent events. All of this rests under an atmosphere that is less a sky than a weight. The pressure at the ground is about 93 times Earth's sea level pressure. The temperature hovers near 737 Kelvin, roughly 464 degrees Celsius, a heat that softens lead. The air is mostly carbon dioxide, with a trace of nitrogen, and the cloud decks high above are thick with droplets of sulfuric acid. Winds aloft race around the planet in a few days, a super rotation that far outpaces the sluggish spin of the solid body beneath. Lightning cracks in the clouds, and at certain wavelengths, sodium and other species glow along the evenings like subtle chemical dusk. Probes that try to breathe that air have to be built like ovens turned inside out. They survive minutes to an hour before the electronics surrender and the housings sag into silence. Still, the planet is not entirely unreachable to gentler designs. In the upper atmosphere, 50 to 60 kilometers above the surface, the pressure and temperature pass briefly through ranges that feel almost familiar. Air dense, but survivable. Warmth, somewhere between midsummer and a hot bath. For a time, this gave rise to sober fantasies of floating laboratories, vast aerostats, trailing instruments, perhaps even habitats tethered to layers where the environment is kindest. The practicality is not obvious. Sulfuric acid is not a hospitable mist, and every system that flies there must resist corrosion and power itself from a sun that is both fierce and filtered. Yet the image of pale balloons drifting over an endless cloud sea is a tender one, and it hangs in the mind like a slow airship in evening light. Venus teaches by contrast. Its present is a runaway greenhouse, a climate tipped so far that oceans, if they ever pooled, must have boiled away, and the carbon once imprisoned in rocks returned to the air. Earth sits in a sweeter balance. Water can stay liquid, carbon cycles through stone, and sea and leaf. But balances are stories we keep telling with heat and time, and planets change their mood when the terms change. Thinking about Venus's furnace is a way of taking Earth's thermostat in hand and feeling the delicacy of its clicks. A neighbor's fate can be sobering and, in a quiet way, protective. The vessels we send continue to widen the map and lengthen the timeline. After Magellan, an ESA orbiter called Venus Express spent 8 fertile years watching the atmosphere breathe and the upper winds whip. A Japanese craft, Akatsuki, recovered from a troubled arrival to circle the planet and make beautiful, long-roll movies of cloud patterns that look like music written in smoke. New proposals listen at the door with instruments tuned to sulfur and heat, to the wavelengths that can see through haze, to the tiny rise and fall of the ground that would signal active volcanism today. Somewhere in the stacks of data, a few volcanoes may already be blinking, a change in brightness here, a fresh flow there, hinting that the planet's fire is not all memory. From a world of heat and cloud, the mind steps home by way of time. Planetary weather is measured in days and millennia. Planetary biographies reach farther. On Earth, the rock record keeps a pulse, and sometimes the beat falters. About 252 million years ago, our biosphere suffered a quiet that was not restful. Nearly 96% of marine species vanished, around 70% of land vertebrates, and even insects so resilient lost about 83% of their lineages. The causes braid together in hypotheses that still weave and unweave. Titanic volcanism, releasing gases enough to change oceans and skies. Continents, assembled into a single heat-catching landmass. Climates tilting hard. Life did not end. It entered a new cadence. From that bottleneck stepped creatures that would shape the next age in bone and thunder, a procession we now call the Mesozoic. Across roughly 186 million years, that age remade the map. The supercontinent Pangaea felt stresses it could not ignore, and the seams began to widen into oceans. Laurasia unfurled to the north, Gondwana to the south, and the crust drifted and thickened and thinned in the slow ballet we read as plate tectonics. Coastlines lengthened. Shallow seas opened and closed like sleepy eyes. Forests reached where deserts had been, and deserts took their turn again. It is comforting, in a humble way, to remember that the ground has currents like the air, only slower. Worlds breathe at many tempos. Some breaths are the spin of a planet, some are the cycling of its air, and some are the seasons of its continents drifting apart. Fall asleep with that rhythm in mind, the near music of orbits and rotations, of cloud winds and lava tides, of extinctions that break and renew, and feel the room around you soften into a landscape that also changes quietly in the space between heartbeats. Planets keep their own time, and nearby the rhythm turns dense and slow. Beneath Venus's clouds, the body of the world is layered like a lullaby sung in low notes, a heavy metallic heart, likely stiffening with age, its dynamo quiet for now, a deep silicate mantle, 3,000 kilometers of hot stone that creeps by degrees, and a crust on top, on average about 16 kilometers thick, strong enough to hold its shapes but too warm and viscous to break into drifting plates the way Earth's skin does. Without that drifting, stresses collect and release in broader sweeps, and the surface records episodes rather than the constant shuffling we know at home. Large, fresh impact craters are fewer than you might expect for a place so exposed. Something heat from below, overturn of the lid, floods of lava, has resurfaced great tracts of the planet in geologically recent time, smoothing over the sharpest scars. Under radar's patient gaze, those tracks resolve into oceans of basalt, frozen flows roof, older terrain. Long, dark plains lie like cooled ink. Where the crust has been pressed and pulled, patterns appear that have no exact parallel elsewhere. Tesserae, the tiles, rise as rugged highlands, ridges crossing ridges at angles, the rock folded and refolded until it keeps the memory of many hands. Coronae gather themselves in wide circles or ovals hundreds of kilometers across, crowned with concentric fractures and radial breaks, as if a dome swelled from below and then relaxed, cracking like the glaze on pottery. Arachnoids thread their fine rings and spokes with a kind of mathematical delicacy. To an untrained eye, the early images seem uniform, storm snow of static and light, but colorized elevation brings out a relief you can almost touch with your thought. Blues for lowlands, ochres for plateaus, ivory for summits. Out of that relief, a continent-length shape emerges at the equator, long and complicated, and bright Aphrodite Terra. Aphrodite stretches some 18,000 kilometers end to end and about 5,000 across, an area comparable to a whole hemisphere of Earth if you cut it cleverly. It is not a single mass with one mood. Rather, it's a braided land of regions called Alpha, Beta, and Gamma, each with its own grammar of ridges, pits, and plains. In the east, Alpha Regio wears its folds tightly, the rock buckled and cross-hatched. Nearby, in and around Aphrodite, broad volcanic edifices rise. One of the tallest known reaches 5 kilometers above its base and stands roughly 8 and a bit kilometers above the planet's mean radius, if you measure from the quiet datum Venusian cartographers agree on. The flanks show channels and collapse pits. The flows are smooth and unpitted by many impacts. Nothing in that landscape smokes now, but the surfaces read young by the planet's slow clock, as though the fire moved there not so long ago. Westward, the tone changes at Beta Regio, a bright, round swell, about 2,500 kilometers across. The ground is pulled in some directions and squeezed in others. Fractures run long and straight until they are curved by doming. Fissures have bled lava that later cooled into smooth sheets. The volcanoes here do not always build neat cones. Some are raised along cracks, fed from below by dikes that pried the crust apart. When you follow those ridges and cuts with your inner fingertip, you can feel the forces that made them, like pressure lines left in a palm. On the western edge of Aphrodite, the land relaxes into Guinevere Planitia, a lowland so broad that plain seems too modest a word. It rolls for thousands of kilometers, but the floor is not featureless. Wrinkle ridges step across it where the ground shortened. Lobate margins mark the edges of old flows. Islands of older, rougher terrain stand up like dark shoals amid a younger sea. In these latitudes and longitudes, orbiters marked candidate landing zones, and in other campaigns, tough metal capsules Venera craft dropped through the clouds elsewhere and tasted the ground for minutes each. Two would-be arrivals in the broader region never made it undone by a sky that squeezes and cooks as if built to test courage. Others, like Venera 9 and 10, reached the surface nearer the equatorial highlands to the west and returned the first sepia-hued views: flat stones, bright sky, a horizon close and low. From those places came the first direct whiff of rock chemistry that looked like basalt, and the first proof that beneath the clouds the world was stone, not ocean or swamp. Farther north, the planet gathers itself into a second highland, Ishtartera, spanning roughly 8,000 kilometers east to west and about 2,500 north to south, a total area only a little larger than Australia. Along its eastern edge rises Maxwell Montes, the highest range on Venus. The crest stands about 11 kilometers above the mean planetary surface, 7 above the surrounding plateau, and the summit is not a spike, but a blocky table, 200 by 400 kilometers of relatively gentle relief, where individual peaks blend into a shared height. Up there, the air is still crushing by our standards, but thinner than at the lowlands. The temperature is cooler by a sliver, around 380 degrees Celsius, and yet on radar, it glows. One reading of that brightness is metallized frost, compounds of lead, bismuth, or sulfides that vaporize from hotter plains and condense out at higher, colder elevations, plating the rocks in a reflective film. It is a winter's tale told in chemistry rather than snow. Between these highlands and their flanking seas of lava, the catalog grows. Sinuous channels, some stretching for thousands of kilometers, snake across plains as though carved by rivers. In truth, they are the paths of very fluid lavas that once ran like oil and cooled into hardened streams. Pancake domes squat in quiet circles, their thick lavas lifted and set down as if by careful hands. Ring fractures and radial dikes intersect like the spokes and rim of a wheel. And all of it is shaped and softened by the lid-like behavior of the lithosphere. No sliding plates, no mid-ocean ridges, no subduction arcs, but an orchestra of doming, sagging, cracking, and the occasional grand resurfacing that resets the count of craters. Overhead, the sky has the weight of an ocean. The pressure at the ground is about 93 times that of Earth's sea level. The temperature steadies near 737 Kelvin, enough to soften lead, enough to heat and hold the air into a dense, heavy calm. Carbon dioxide makes nearly all of that air. Nitrogen brings a small share. Higher up, clouds of sulfuric acid are stacked in decks that circle the planet. Winds in those decks race around the world in a matter of days, a super rotation that leaves the slow retrograde spin of the surface far behind. Lightning mutters in the clouds. Sodium and other species glow faintly along the limb at certain wavelengths, a chemical dusk at the edge of day. Machines built to touch that world must be ovens turned inside out, their electronics sealed and cooled, their metals chosen to stay themselves in a place that overwhelms definition. Most that have tried have fallen silent within an hour. They do not fail. They are spent. There is a difference, and it is noble. And yet there is a gentler layer somewhere between 50 and 60 kilometers above the surface, where the air pressure is closer to a mountain day on Earth and the temperatures are merely hot. For a time, engineers and dreamers ran threads from that layer into possibility. Long-lived balloons drifting on stable winds, gondolas tucked from acid by smart skins, laboratories listening to the ground with radar and to the sky with chemistry. The practicality is hard. Energy must be gathered and stored. Structures must resist corrosion. Communications must pierce the clouds without fuss. But the image is calm and persuasive. Pale aerostats crossing an endless cream-colored sea, instruments murmuring, a window opening to a sky no human eye has seen unfiltered. Whether by balloons or tougher landers or instruments tuned to watch from orbit, the planet's story will lengthen. The surface waits with patience that outlasts us, and secrets on Venus keep the manner of geologic time. They yield when asked the right questions, softly and often. A neighbor does not exist to be conquered, only to be understood well enough that its presence is no longer an abstraction. That understanding, too, is a kind of climate we can live in. The mind, softened by cloud and heat, steps from space to time without breaking the drift. Our own planet keeps archives in rock and bone, and there are pages where the ink darkens. About 252 million years ago, the world passed through a narrowing the Permian-Triassic event, when oceans emptied of nearly 96% of their known species. Land lost about 70% of its vertebrates, and even insects suffered like never before. Causes weave, volcanoes that poured greenhouse gases and aerosols into air and sea, continents gathered into one heat-catching mass, oceans that lost their breath, climates that swung too wide. The pulse slowed, but it did not stop. When it resumed, the tempo had changed. The Mesozoic, about 186 million years of altered rhythm, opened like a long, warm season. The great continent Pangaea began to ease apart along lines of weakness, at first into two broad rafts, Laurasia in the north and Gondwana in the south, and then into pieces that would become our familiar map. Rifts turned to newborn seas, coastlines multiplied, currents woke and wandered. There were no permanent ice sheets, even at the poles for long stretches. Heat moved differently. Rain fell in bands and deserts widened. Then seas fingered inland again, and the bands shifted in reply. Life tracked those patterns with its own migrations and inventions. The first span of that era, the Triassic, roughly 51 million years, feels, in hindsight, like the quiet between storms, though the ground was not still. The air likely carried less oxygen than today, perhaps 10 to 15% for much of the time, then rising toward values nearer our own by the late Triassic into the earliest Jurassic. Whether that rise owed more to changes in plant communities, to mountain building that fed the weathering pump, or to shifts in ocean circulation and burial of organic carbon, is a matter for careful argument, but the arc is clear enough for a bedtime chart. Over tens of millions of years, breath came easier. Plants wrote the first lines of the new script. Prehistoric seed ferns, glossopterids, and their kin held on in some corners but ceded the main stage to gymnosperms better suited to drier, warmer continents. Conifers with their resin and needles, ginkgos with their fans, cycads lifting armored crowns above tough trunks. Forests spread along rivers in some places and leaned back to scrub in others, and between them the wind carried pollen like fine, patient snow. In the seas that had been so emptied, new swimmers learned the old grammar of pursuit and flight. Turtles took to the water in their early forms. Teleost fishes began the long experiment in bony elegance. Among the reptiles, a lineage found the ocean easy to inhabit, with bodies tuned for speed. Ichthyosaurs, fish lizards, arrived in shapes that would later refine into torpedoes, but at first, some were long and almost eel-like, with flexible tails and broad paddles in place of hands. Symbospondylus, which swam between about 240 and 210 million years ago, could reach lengths of 6 to 10 meters. A predator, not of monsters then, but of fish and cephalopods, a strong, quiet blade moving through green light. On land, the cast was mixed and inventive. Rhynchosaurus and its cousins scuttled and browsed. Large temnospondyle amphibians lounged in river shallows, crocodile-long and frog-kin in their bones. Early members of the crocodile lineage themselves hurried on long legs. Small, gracile archosaurs stretched into forms that would lead to pterosaurs in the air, and, later, to the birdline among the theropods. Midway through the Triassic, a branch of the archosaur tree gave rise to true dinosaurs, at first modest in size, quick and light, threading their way among older guilds. They did not take over immediately. They survived, diversified, tested strategies, and only toward the end of the period, as climates shifted and oxygen rose and competitors faded, did they begin to dominate. Even then, dominance is a mosaic on the ground, pockets of abundance, corridors of change, and always the local weather of chance. It is tempting to think only of the giants, the thunder lizards of cinema, all appetite and armored tail. The ground truth is more intimate. Alongside future royalty, lived creatures with the proportions of a hand or an arm, busy with their own quieter empires. Among them, near the turn from Triassic to Jurassic around 200 million years ago, scurried Oligocophus, kin to the tritylodontids, mammal-like reptiles with chewing teeth arranged for shredding plants. Picture a lithe, weasel-length body, perhaps half a meter nose to tail, warm-blooded, furred, herbivorous, bright-eyed. The jaws worked sideways as well as up and down. The limbs were made for quick starts and the kind of tunneling that leaves narrow doors. Fossils tell of their presence in what is now North America, Europe, and China. The skeleton suggests that the young were tiny at birth. The soft tissues are lost to stone, but the logic of the lineage and the structure of the bones whisper of milk. You can imagine a burrow lined with dry leaves, a parent's warm breath, a dusk life lived below the notice of the large. Competition tightens when habitats shift. As the Jurassic opened, new plant communities rose, new predators refined their tools, and some of the small herbivores of the old design slipped away. Oligocophus likely vanished early in that new age, not with drama, but with the steady arithmetic of ecology. Too little food, too many mouths, evolved to eat the same leaves more efficiently. Their absence is not a failure, it is a chapter turn. They stand in the fossil record as clear waypoints on the path toward mammals, demonstrating warm blood, parental care, and a social intelligence carried not in spectacle, but in the tender routines that make nights survivable. Hold all these tempos together, Venus resurfacing in long, fiery breaths, Earth reassembling its faunas after a great hush, little bodies inventing their own ways to stay warm, and your own breath finds a quieter rate. The universe does not move in lockstep, it sways. The planets turn, the continents drift, atmospheres pulse with light and storm, and life learns the beat that is available. In a room made still by night, that is enough. The rhythms outside become a kindness inside, a reminder that change can be vast and still feel, at heart, like a lullaby. The beat continues, and a page turns. At the boundary between the Triassic and the Jurassic, the rhythm caught and slipped amphibians in whole lineages, faded. Some archosaurs and reptiles went quiet. Plants rewrote their ranges. Volcanoes may have loaded the air and seas with gases and ash. Shorelines wandered as oceans rose and fell. Climates lurched. Whatever the braid of causes, the effect was a clearing of space. In those open niches, dinosaurs already present and experimenting found room to settle in, to stretch, to try on more of the world's roles. The Jurassic that followed lasted on the order of 56 million years, from about 201 to 145 million years ago. Pangea, that grand stitched-together land, finished the art of becoming many. Rifts opened into long, warm seaways, continents to be stood farther apart, and shallow shelves wrapped them like fringing lagoons. On maps drawn near the end of the period, you'd recognize outlines, but you'd be surprised by where they sit. Isolation does its slow work. Life on one raft takes a path that its cousins on another never see. Air and rain found a new accord. The climate, for most of the time, was warm and generous with moisture, a green theater. Tropic forests spread where today we picture deserts. In higher latitudes, milder woods held on. Ferns lifted lace from the understory. Cycads raised armored rosettes. Ginkgos flashed their flat fans, and conifers kin to cypress and pine threw long shadows. In their shade, insects hummed the same eternal songs, and the ground steamed with the breath of the living. Dinosaurs filled the open rooms with variety. Quick cat-sized runners threaded through ferns. Heavy-bellied browsers shouldered through trunks. And in the clearings, the tallest grazers ever to live bent entire trees like grass. Names we learn as children: Brachiosaurus, Brontosaurus, Diplodocus, belong to this era's long-necked families. Later, in the broader clan of titanosaurs, some would reach lengths of 25 meters or more and weights measured in tens of tons. At the hips, an old idea once suggested a second brain, a swelling in the spinal canal, as though thought had pooled there. The romance has softened with evidence. That space likely hosted a glycogen body, an energy store, not a second seat of will. Even corrections can be gentle. The truth is still wondrous. Other experiments ran alongside. Early mammals, small, warm, alert, tested nighttime, dug into soil, learned to nurse and to keep their young in hidden places. Reptiles split and specialized. Arthropods went about their unending business with quiet mastery. In the oceans, bivalves paved the seafloor like living shingles. The role of swift, top predator fell to marine reptiles, ichthyosaurs built for speed, plesiosaurs with long, searching necks, or deep-chested, short-necked power. Across the water, evolution redrew the same outline with different lines. Compare two ichthyosaurs, and you can hear the change. Symbospondylus, early and eel-bodied, 6 to 10 meters long, with a flexible tail and a head not yet pressed to hydrodynamic purity. And, much later, Ophthalmosaurus, the torpedo-refined sleek trunk, strong vertical tail, a dolphin's grace in stone. Ophthalmosaurus breathed air, could stay below for on the order of 20 minutes, sprint beyond 7 kilometers an hour, and likely dive a few hundred meters into blue-green quiet. Its eyes were huge and braced with a bony sclerotic ring, a natural pressure suit for vision. Squid and other soft-bodied prey wrote their presence in its teeth and in the shapes of its ribs. Time drifted onward to the Cretaceous, the longest chapter of the Mesozoic, beginning around 145 million years ago and running for almost 80. Continents kept sliding. India loosened from Africa and raced toward Asia. South America leaned west. By the late pages, the outlines of Africa, Australia, Greenland, and the Americas would look familiar, and Europe and Asia would be carving a complicated border. The climate's mood shifted. Cool spells opened the act. Then, a stretch of deeper warmth arrived roughly between 185 million years ago. Then cooling pressed again toward the close. If the Jurassic was a chorus of conifers, the Cretaceous added a new instrument: flowering plants. They learned to package energy in seeds and to court insects with color and scent. Forests diversified. Shrubs took their places. The earliest grasses began to whisper on floodplains. Turf formed, soils thickened, and the menu for small herbivores expanded. Mammals diversified in parallel, tiny atherians and metatherians testing teeth and hands, sketching the blueprints that would much later become hoofed grazers. nimble hunters, primate kin. Now and then, the veil lifts on a particular life. Repenomamus, about 125 million years ago, was a mammal the size of a small dog, up to a meter long, perhaps a dozen kilograms of muscle and appetite. The skull shows a predatory dentition. The limbs suggest a sturdy, ground-hugging gait. One fossil arrives with a hush, bones of a young dinosaur gathered in its abdominal space. Whether that meal was hunted or scavenged matters less than the simple fact it conveys. Mammals were not only furtive seed-eaters under giant feet, some were bold enough to take meat when they could. The seas, meanwhile, changed their cast. Mid-Cretaceous oceans suffered episodes when deep waters grew short of oxygen, oceanic anoxic events written in black shales and isotope swings. Such intervals reshaped food webs. Ichthyosaurs, long the greyhounds of the sea, declined and vanished by the late Cretaceous. Mosasaurs, powerful lizards turned marine, rose toward dominance. Plesiosaurs held on in varied forms. Volcanic outgassing, circulation shifts, seafloor spreading, many levers were at work. The result, for a while, was a quieter deep and a different balance among the hunters. At high latitudes, the story took on a polar shade. In what is now northern Alaska, above the Arctic Circle, around 70 million years ago, lived Nanuqsaurus, polar bear lizard, kin to Tyrannosaurus, but scaled to a leaner pantry. 6 meters in length, 1,000 kilograms give or take, feathered and warm-blooded, it ran hot in a cold world. Feathers, layered like down in pennants, would have kept heat close. A fast metabolism, bird-like in tempo, would have kept the engine humming. In long winters, when night lingered for months, smell and hearing and low-light vision likely stood in for color and sun. The skull tells of large olfactory bulbs. The eyes are set to harvest what light there was. Summer came brief and cool. Nests may have needed extra warmth beyond the pale sun. Care of young, brooding, guarding, bringing food threads through many theropod stories, and brains proportionally larger than those of many reptiles hint at the behaviors that go with such care. Even such careful designs can be vulnerable to a larger turn of the wheel. About 66 million years ago, a bolide struck near what we call Chicxulub, and the planet's own volcanoes were in an active mood. The Cretaceous-Paleogene boundary carries a signature layer of iridium-rich dust. Shocked minerals, spherules, fallen like glass rain. In the years that followed, skies dimmed, plants struggled, food chains snapped. Non-avian dinosaurs stepped off the stage, along with pterosaurs and many marine reptiles. Ammonites closed their shells on the last page of their long story. Birds, the dinosaurs that learned to fly and never forgot, threaded through the bottleneck. Mammals, long diverse but mostly small, moved into rooms that were finally open. Forests regrew. Rivers resumed their gossip. The world's breath steadied and then took up a different melody. From that quieter beginning, the Cenozoic unfolded primates, finding grasp and gaze. Carnivores refining the grammar of pursuit. Hoofed mammals learning to run on grasslands that spread in earnest much later. Somewhere near the end of this long drift, a primate with hands good at making and a mind good at imagining began to ask where it was. The names we've given ourselves are many. The one in common use carries hope and hazard in equal measure. The story is not a coronation. It is an invitation to attention. We are part of the same slow music, continents still rearranging, climate still balancing, oceans still breathing, stars still rising over a sleeping room. Let your own breathing match what you've learned to hear the pulse of ages, the hush after storms, the steadying warmth of knowledge held without hurry, and feel how even the largest changes can be set gently on the night. The new tempo opened softly after the great hush. When the dust settled from the Cretaceous-Paleogene break, a different era took the stage, the Cenozoic, beginning 66 million years ago, and still unfolding like a long, calm breath. Earth shifted its weight and found new postures. India slipped across open water and pressed into Asia, lifting rock into the bright air to become the Himalayas, snow catching on their shoulders, even as the world ran warmer than now. Far to the south, Antarctica drew a white cloak around itself, an ice shield thickening year by steady year. Continents exhaled and rearranged. Seas found new rooms. Winds learned fresh routes across the skin of the planet. In the first 10 million years, life recovered with a patience that looks, from afar, like urgency. Mammals, small for so long, flared into forms that tested the open spaces left by the vanished giants. Nimble hunters and rooters, runners and climbers, night listeners and day foragers took their places. Some names arrive like soft footfalls in the Paleogene night. Andrewsarchus, long-skulled and opportunistic, along windy coasts. Intricotherium, also called Paraceratherium, rising into a hornless giant, browsing treetops with a careful mouth. Archaeocete whales, learning the grammar of the sea, limbs turning to flippers as they took deeper breaths and longer dives. Some of these presences faded, others adapted. All of them were sentences in a new chapter written in warm air and green shade. Around 23 million years ago, the light changed and the Neogene began. Cooling advanced by inches, not leaps. Ice widened its claim. Tropical belts narrowed, and the conversation between air and ocean found new routes. The Alps and the Andes rose higher. Sea level drew back. Between Africa and Europe, the Mediterranean basin at times stood cut off from the Atlantic, a giant bowl under a high sun. In that isolation, water left faster than rivers could replace it. Salts crusted the bed. Air grew heavy in the depths, more than half again the usual pressure, and heat pooled like breath held too long. A quiet, lifeless plain stretched where a blue sea had been. The Miocene, long within the Neogene, scattered the earth with striking presences. Forests and grasslands braided into mosaics. Winds ferried seeds to new latitudes. In Asian rainforests, a giant ape, Gigantopithecus, kin to orangutans, stood immense among bamboo and fig. On open ground, great predators shouldered between scavenging and the hunt, testing herds that learned to run with heads held low. Offshore, Megalodon patrolled as a moving cliff of appetite, the largest macro-predatory shark the planet would host. Life kept time with shifting climates, sometimes close, sometimes far, always finding niches in the slow dance of warmth and dryness. A little more than 5 million years ago, a threshold failed. The rocky sill at Gibraltar gave way, and the Atlantic rushed back into the emptied basins. Water thundered down canyons and across flats, filling the Mediterranean not in epochs, but in a handful of seasons. The Zanclean flood reset a sea and turned deserts to blue, burying stacks of salt beneath sand and silt. With the refill, the Pliocene opened. Continents had drifted into positions our eyes would recognize on a modern map, though a few seams were unfinished. North and South America were not yet fully joined. The isthmus between them would rise soon. Global temperature in the early Pliocene ran a couple of degrees warmer than today's average, but warmth wore many faces. The tropics felt familiar, while the far north lived in a different script. The Arctic was not locked in permanent ice, and dense conifer forests reached toward high latitudes. Sea level stood higher, pushing coastlines inland and laying a bright edge over continental shelves. In that climate, somewhere along river edges and in broken woodland, our earliest known relatives were making small, consequential decisions. Fossils of Sahelanthropus, Orrerin, and Ardipithecus, dating between about 7 and 4 million years, show hips and feet beginning to compromise with bipedal balance, hands still suited to branches, skulls with room enough for minds that could plan a little and remember a little longer. Forest did not vanish at once, but it thinned. Grassy savannas pressed in from the margins, and paths opened between islands of shade. The world asked for a new way of moving through it. What tilted the lesson plan was part geography, part wind. As the Isthmus of Panama sealed between the Americas around 3 million years ago, ocean currents were rerouted. Heat traded pathways. The Atlantic and Pacific could no longer whisper directly at low latitudes. At the same time, mountains lifted higher in many ranges and leaned the winds. Ice found new footholds in Greenland and around the pole. Africa's forests retreated in patches and sun-touched ground. It had not warmed in ages. Where shade had made ladders, grasses now made horizons. The old talents still mattered, but new ones rose with the dust. Treetops had been safe balconies for ages, high, shaded, generous. But when the canopy broke and the ground widened, survival asked for different tricks. Standing tall helped a watcher see farther across the grass and gave hands back to carry, to brandish, to shape. Stones flaked to an edge could open bone and turn marrow into a meal. Sticks could probe and pry. Alone, a primate on the plain is a nervous heartbeat. Together, a band can bluff a hyena, test a carcass, share the fat and the story that goes with it. Coordination, who circles, who calls, who waits, became as important as teeth. Language did not arrive at once, but the need to time movements together made room for it. Meat was not the only prize. Tubers and hard seeds, scavenged or dug, demanded teeth and tools and patience. Diets widened. Omnivory asked for inventiveness over specialization. Walking freed the arms. Shoulders loosened. Thumbs, already deft, grew ambitious. Fire, when finally borrowed from lightning and then kept, stitched a zone of protection through the night and turned food into something gentler on the gut and quicker for the brain to borrow. In that steady flicker, young learned by imitation the oldest school while elders shaped memory into method. Practice made culture, and culture thickened the thread that tied one dusk to the next. Over spans measured by lake mud and volcanic ash, bodies answered to this new syllabus. Knees angled to keep the gait efficient. Feet traded grasp for spring and arch. Pelvises reshaped for balance and birth. Teeth and jaws adjusted to tougher plants and occasional meat. And somewhere in this gentle arms race with climate and landscape, the habit of working in small bands with shared intent deepened. A kind of mind that can hold another's viewpoint, can anticipate, can wait. Attention learned to stretch. Care learned to linger. By the time the Pliocene yielded to colder chapters, the line that leads to us had a clearer outline. Australopithecus appears in the record across Africa between about 4.2 and 1.8 million years ago. Bodies not tall but lithe, arms still long, hands capable, hips and feet tuned for walking the distance between shade and water. They left footprints across damp volcanic ash at Laetoli that still read as a family, crossing a small stride beside a larger, both heels settling into dust that hardened into memory. The prints say nothing and everything at once. We were here. We moved together. The day was warm. The ash was soft. Let your breath settle with theirs. The Cenozoic does not rush. Continents grind and buckle. Seas empty and spill back. Climates lean warm, then cool, then warm. Forests open. Grasslands write their wide, pale sentences. Through it all, life adjusts and tries again. The map outside the window is quieter than the fossil record, but it belongs to the same music. The past does not recede. It becomes the ground you walk on. And in that thought there is comfort fit for night. Change, even the kind that remakes oceans and mountains, can be carried gently, one sleeping breath at a time. The music carries us outward, and a red world rises like an ember beyond the evening trees. Mars is never truly alone up there. A quiet fleet keeps vigil, orbiters tracing patient loops, rovers tasting dust and light, so we can read its weather and its scars without breaking the hush. In the west of that world stands a mountain so broad it feels like a horizon, pretending to be a hill. Olympus Mons lifts its dark shield about 26 kilometers above the plains, roughly 2.5 Everests, gently stacked and spreads for some 600 kilometers, wide enough to swallow a country whole. Layer upon layer of cooled lava built it, each flow settling like a page laid on another. And because Mars lacks shifting plates to tug hot spots along, the same vents could feed the same slopes for ages, letting the single volcano grow vast, instead of being smudged into a chain. Near the crown, the ground gives way into a complex of calderas, 6 great bowls overlapped like spilled moons, about 85 kilometers across and 3 kilometers deep. The slopes leading there are deceptively kind, averaging only a few degrees, a grade your legs might forgive on a long walk. The edges are not so gentle. Around the skirt, cliffs drop in places by up to 7 kilometers, an abruptness that feels almost theatrical in such thin air. At the summit, the atmosphere is 50 times more rarefied than at the base. On the plains, Mars's air is already about 1 part in 160 of Earth's sea level pressure. Parachutes struggle to bite in such lightness, and a lander falling toward those heights would find little to grasp. Whether ancient shoreline winds or ice and dust working together helped sculpt those towering escarpments, the exact recipe is part of the planet's quiet, ongoing riddle. Walk away from the mountain in your mind, and the ground sags into ridges upon ridges, isolated knobs, and pale aprons that run hundreds to 1,000 kilometers out. Some look like the slumped remains of lava that once hummed with heat. Some wear the delicate combing of ice or dust that moved for seasons and then stayed. Southeast, the land gathers and lifts again into Tharsis, a volcanic upland so extensive it feels less like a region and more like a mood. An ancient swell of crust, about 10 kilometers above the surrounding plains, old as 3.7 billion years by the best readings. Here, shield volcanoes overlap, their broad backs pressed together, each one a library of eruptions. For ages, they released gases into the sky: carbon dioxide, water vapor, sulfurous breaths that thickened the air by degrees compared to today and helped warm what sunlight could reach. Models sketched that story with care: an atmosphere once far denser than the trembling veil we measure now, enough at times to let liquid water linger and to let clouds write slower sentences. Among Tharsis' giants, Arsia Mons rises nearly 19 kilometers, with a summit caldera more than 100 kilometers wide and flanks that stretch beyond 400. Certain seasons bring a fragile spectacle. When sunlight warms the slopes, winds lift air up the mountainside and paint a long, bright streamer, a high, elongated cloud that can extend tens of kilometers and then fray into the blue-black. It appears and fades like a breath tethered to the mountain's daily pulse. Across the plateau, vertical pits puncture the basalt, dark circular mouths, tens to hundreds of meters across, some dropping deeper than cameras have yet measured, likely collapses where lava once tunneled and then withdrew, leaving ceilings to fall in. Such skylights hint at caverns that could shield future instruments, even fragile microbes, from radiation and cold. Lean east, and the upland unrolls into absence, an open cut in the crust so long it bends with the planet. Valles Marineris runs for roughly 4,500 kilometers, a continent's worth of canyon, as much as 600 kilometers wide and more than 11 kilometers deep in places. Stand on one rim in your thought, and the far wall is lost to hazy distance. The floor is tiered with benches and terraces, many of them layered like pages, pressed flat. In central and western reaches those layers look, from orbit, akin to sediments that settle in still water, thin beds, repeating, interrupted by thicker, more resistant bands. Whether all were laid by lakes or seas, or some by volcanic ash and wind reworked by time, the slopes carry the signature of deposition as clearly as lines show in a fingerprint. To the east, the canyons braid into labyrinths, small chasms, mesas, broken plateaus like a shattered honeycomb. The origin story holds several verses, rifting as the Tharsis bulge pulled the crust apart, lava withdrawing from beneath and leaving the roof to fail, groundwater bursting out to help widen and smooth. Perhaps even the far echo of a giant impact elsewhere, focusing fractures along this arc. Each idea adds instruments to the same song of extension and collapse. North from there, the land eases into the great northern lowlands. Utopia Planitia lies as a broad, round basin, about 3,300 kilometers across, quiet, flat, and deceivingly simple from altitude. It has been a practical harbor for visitors. Viking II came here in 1979 and felt the soil under its pads. In our own century, China's Zhurong rolled over this plain, tasting dust and listening for whispers below. Radar from orbit has mapped rich stores of water ice mixed with dust beneath parts of the surface, sometimes only a handful of meters down, sometimes deeper, a locked pantry in a cold house. Not every scoop reaches that frost. The layered skin is variable, and patience is part of the craft. To the north of Utopia, the lowlands widen into Vastitas Borealis, a basin that spans about 40% of the planet's face, a floor that may once have been shoreline if ancient seas truly pooled here. Swing southwest and you meet the rim of Isidis Planitia, a broad impact hollow whose western edge holds a smaller bowl named Jezero. There, deltas preserved in stone call to the eye with the calm of old river mouths, fans of sediment, laid down where water slowed, their geometry a fossil of flow. That is where Perseverance landed in February 2021, with a small, brave helicopter called Ingenuity tucked beneath its belly. The rover has since cored and cached samples from rocks that show the touch of water minerals altered in ways that require liquid, textures that speak of cycles, wet and dry. The helicopter skimmed the thin air and proved that even in a place where the wind is like breath in a bell jar, a small rotor can pull enough on nothing to fly. The broader age those rocks inhabit is called the Hesperian, beginning around 3.5 billion years ago and lasting on the scale of 1 billion years. It was a time when volcanism was common, and water may have been episodic lakes, filling and draining, rivers cutting and then stopping, glaciers creeping in cold spells. The air then was thicker than today's, perhaps by a wide margin, though how warm the days ran is still whispered in the argument between models and minerals. What's certain is that Mars grew colder and drier with time. As its interior cooled, its field faded, and the solar wind had its quiet way with the upper atmosphere, stealing lighter molecules to space. Layer by layer, the sky thinned until parachutes had to be clever and turbulence rare. Yet even in such austerity, the planet keeps a generous archive. In canyon walls and crater rims, in deltas and dunes, in the chemistry of salts and clays, there are chapters written by water and fire and wind. A rover's drill and a scoop do not feel like pens, but the samples they set aside are sentences waiting to be read at home, with instruments too delicate to fly. The plan to fetch them is itself a story of patience, a relay race over years to bring a handful of Mars into clean rooms where we can ask questions softly and let the rocks answer at their own pace. Let your thoughts linger at the edge of a Martian escarpment where sunrise arrives in a thin copper line. Down in Valles Marineris, the shadow keeps its cool for hours. On Olympus Mons, dawn pours across a plain so broad the curve of the world hides it from itself. Wind lifts and settles dust in nervous scrollwork. Somewhere in Utopia, a lander sleeps under a faint blanket of rust. Somewhere in Jezero, wheels press a new track into old sediment, and then the track softens at the edges, as if the crater prefers its quiet. This is not a hostile world so much as a deeply reserved one. When we read it patiently, with instruments that listen more than they insist, it opens into legibility. And legible things, even when they are austere, can be lived with in the mind, held like a cool stone in the hand until the hand warms it. Between Mars and Jupiter, the night thins into a wide, quiet river of stone. It isn't a cluttered maze the movies promise, but a hushed expanse, sparsely peopled by small worlds that keep their distance and their dignity. Astronomers have cataloged hundreds of thousands of them, each with a number and a name, and there may be 1 million or more in all. Dust sifts between them, so fine it behaves like light's own memory. When the geometry is kind and the sky is dark, that dust sketches a faint, sloping pillar on the horizon, the zodiacal light, soft as breath on a mirror. The story opened 2 centuries ago with a bright dot that refused to show a disk. In 1801, Ceres stepped onto the stage, modest and confusing, first called a planet and then demoted as other similar points joined it. Asteroids, star-like bodies, the new word went shy stones that share an orbiting province rather than a single identity. For a time, people imagined a shattered planet's graveyard here. The numbers have since made the case gentler. Even added together, these objects total only a few percent of our moon's mass, too little to build a proper world, and the deep tug of Jupiter's gravity shakes the region so persistently that anything large is coaxed into fragments. In models, the biggest bodies that ever cohered in this zone rarely exceeded 1,000 kilometers across before the giant's pull stirred their paths into collisions. The river still holds those echoes. Families of asteroids linger with similar colors and orbit sibling shards from ancient breakups, spread out like petals in slow motion. The main belt's broad address runs roughly from 2.06 to 3.27 astronomical units from the Sun, but within it, Jupiter's rhythms carve tidy absences. At certain resonances ratios where an asteroid loops the Sun in, say, 3 orbits, for every one of Jupiter's, the gas giant's periodic nudge adds up and hollows out lanes. We call them Kirkwood gaps. One sits near 2.5 AU, another near 2.82 AU. They mark the music more than the map. On the belt's outer avenues move Ceres, the round one, the only dwarf planet among these fractured neighbors. Nearly 940 kilometers wide and about a third of the belt's total mass, it is large enough for its gravity to pull itself into a globe. Its path ranges from about 2.5 AU at perihelion to nearly 2.9 AU at aphelion. Its temperatures hover far below freezing on average, on the order of 100 degrees Celsius beneath zero, with occasional milder readings, still cold enough to bite. Inside, scientists infer a rocky core cloaked in a 100-kilometer thick cryomantle, where water ice makes up a startling fraction of volume. Ceres carries, in miniature, the logic of a differentiated world: layers, chemistry, weather of the slowest kind. Closer encircles Vesta, brightest of the asteroids, and, under very dark skies, a thing you can sometimes meet with the naked eye. About 525 kilometers across, and graced with a high albedo surface that reflects nearly half the sunlight it receives, Vesta travels an elongated track between roughly 2.15 and 2.57 AU, completing a year in a little more than 3.5 Earth years. Beneath its battered crust lies the structure of a little planet: an iron-nickel core, a silicate mantle, and a basaltic skin. Temperatures on that skin swing between deep, cold, and merely bitter. In the southern hemisphere, one wound defines the landscape: Rhea Silvia, an impact basin about 550 kilometers wide. So wide, its rim nearly reaches the asteroid's own edges. At its center rises a mountain more than 20 kilometers tall, among the loftiest peaks in the solar system. That strike seems to have ejected a rain of fragments that now populate the Vesta family. Tens of thousands of bodies that carry Vesta's spectral fingerprint and account for a notable portion of the belt's population. Not all remnants hold together as neatly. Some rebuild themselves from shards into what astronomers affectionately call rubble piles, aggregates held by gravity more than by internal strength, laced with voids. 87. Sylvia appears to be one of these loosely knit worlds, three-lobed in outline, roughly 384 times 262 times 232 kilometers, and of such low average density that empty space must lace its interior. Around it drift 2 small moons, Romulus and Remus, likely born from the same collisional past. Their surfaces are dark, Their shapes are irregular. Their orbits tell a patient tale of mutual capture and settling. Elsewhere, the belt hosts elders that may be surviving protoplanets, bodies that started down the road to planethood and then paused when Jupiter's hand shook the table. 2 Pallas, discovered soon after Ceres, is a case in point, about 512 kilometers in mean diameter, on an orbit more steeply tilted than most, some 35 degrees to the ecliptic, and stretched from about 2.1 to 3.4 AU. That inclination makes close flybys by spacecraft a trickier proposition. The payoff for study would be large, since compositions suggest ordinary silicate rocks mixed with darker, more carbon-rich material, and perhaps bound water. Pallas's face is heavily cratered, a palimpsest of strikes that reach back to the solar system's sleepless youth. In the other direction, darker, quieter, lies 704, Interamnia, a sizable, irregular world, some 360 kilometers across, that swallows light rather than throwing it back. Its surface albedo is so low that it absorbs the lion's share of what falls on it, as though painted in soot. Spectrally, it sits among rare, featureless types, F-class, carbonaceous, ancient, and reticent. Its density points to a mixture that could include a rocky core under a chilled shell with ice and dust. It walks an orbit that ranges roughly between 2.5 and 3.5 AU, threading paths that cross those of bigger bodies in projection and yet almost never in truth, because the belt is all breadth and very little crowd. This is the quiet surprise: distance. The average separation between even the larger asteroids can be measured in millions of kilometers. Spacecraft do not dodge boulders on their way through. They sail under wide skies and plan meticulously to meet even one target. Collisions still happen very rarely, by human reckoning, regularly by geologic time. Every few million to tens of millions of years, impacts freshen a surface, birth a family, seed meteorites that will, much later, hiss through an atmosphere and pepper a desert or an ice field with small testimonies from the belt. A few emissaries from Earth have circled and tasted these bodies up close. NASA's Dawn spacecraft, with its patient ion engines, slipped into orbit around Vesta in 2011 and read its gravity fields, its craters, its composition. Then it coasted outward to Ceres in 2015 and found bright salt deposits and hints of subsurface brines, a chemistry that makes even a cold, small world feel geologically eloquent. Newer craft take longer routes. Lucy is on a sweeping tour designed for Jupiter's Trojan swarms, but along the way, it will nod to a main belt object named for the paleoanthropologist Donald Johanson. These are not conquests. They are conversations slow, carefully phrased, willing to pause for years between sentences. For science, the belt is a time capsule. Its rocks preserve textures from the protoplanetary disk, the heat of short-lived radioisotopes, the sorting of metals and silicates, the hydration of minerals where water once kept company with stone. Meteorites on our shelves, matched to spectra of families in space, let us triangulate histories: which parent body, which break, which passage through sunlight and cold. For practice, the belt is a proving ground. A future in which spacecraft refuel or harvest materials away from Earth will have to learn the etiquette of microgravity and the engineering of gentle touch. Rubble piles punish haste and reward understanding. Anchors must be designed more like hugs than harpoons. drills must sip rather than shove. Through a small telescope, the belt vanishes into anonymity. Even the biggest members are points. Through radar, spectra, occultations, and visits, individuality blooms. Some spin like anxious tops. Some tumble. Some wear moons. Some carry grooves like a phonograph. Some are monoliths. Most are mosaics. Compositions range from bright basaltic crusts to dark carbon-rich mantles so ancient they seem older than memory. The pattern across them all is not drama but patience. Formation, disruption, reassembly, gentle erosion in the slowest possible weather, sunlight and vacuum, dust and time. If you listen for it, you can hear how this stone river ties back to worlds we've already met. Vesta's basalt speaks of internal heat and the first steps toward differentiation, like a miniature, arrested Mars. Ceres's ice and salts echo the outer solar system's recipe, a cousin's pantry found closer in. Pallas's tilt hints at early shoves and near misses when giants migrated and resonances swept. Sylvia's hollowness explains why landing on small bodies feels like learning a new kind of balance, one where your own push can set the world and you drifting apart. At certain dawns, zodiacal light raises its faint obelisk ahead of the sun and points along the ecliptic like a path lightly chalked on the sky. That sheen is the asteroid belt's handwriting, not loud, but persistent. Between red Mars and banded Jupiter, an archive keeps turning in darkness, page by porous page. Stones remember the heat that shaped them. Families drift like slow constellations. Gaps mark a silent conversation with a distant giant. Sleep takes the hint. The space between things is not emptiness, but room enough for a million small stories to keep time. Between those slow drifting stones and the banded giant beyond them, the question turns intimate. What does it actually take for life to wake and keep going? The recipe always sounds simple. In daylight, liquid water, a steady energy source, a pantry of useful chemicals. But in the quiet of night, it feels more like a mood. Not too hot, not too cold, not too sterile, not too violent. Earth checks all those boxes by habit. Mars may have checked them once and still hints at old wet pages. Farther out, where sunlight thins, the next good candidates hide their warmth under ice and keep their chemistry in the dark, close to a world that is itself unlikely to host anything living. Jupiter is grand beyond metaphor, a globe of hydrogen and helium so large it tugs the solar system's center of mass off the sun's skin. Its atmosphere holds methane and ammonia, water and sulfur species, storms taller than mountains, lightning that writes its name in radio. But there is no clean floor to stand on, only deeper and deeper layers pressed to unimaginable densities and heated to incandescent rage. Biology, as we know how to imagine it, would be forced apart there. The hope slips. Instead, to the company Jupiter keeps the 4 bright attendants Galileo first saw in 1610, each a world with its own weather of stone and ice. Io with fire, Europa with an ocean under glass, Ganymede with a magnetic heart, Callisto with a memory of collisions almost as old as time. Start with the largest. Ganymede could bully Mercury for size and win. Its radius tops our innermost planet by a quiet margin, and its mass doubles that of our moon. Beneath a crust cold as powdered glass sits a layered interior, and at the center, a liquid metal core turns enough to make a magnetosphere, the only moon in the solar system with that personal shield. Galileo's spacecraft data suggest an ocean tucked below the ice, salty, stacked in tiers by density, threaded with minerals. Imagine water in chapters: liquid, high-pressure ices, more liquid, more ice, all shaped by salt and temperature. A thin oxygen exosphere brushes the surface, born when ultraviolet light splits water and the lighter hydrogen drifts away. Spectra, read by patient instruments, pick out carbon dioxide, sulfur compounds, sulfates, organic traces. Whether these are crumbs from the ocean below or decorations from space is unsettled, but the list itself is a comfort. Variety is the beginning of interesting chemistry. Callisto waits farther out, quiet and cratered, the second largest of the four and the least bothered by Jupiter's tides. Its surface is an archive of impacts. Beneath the pitted skin, models point to a deep, briny ocean roofed by tens of kilometers of ice. Ammonia and salts could keep that water liquid at temperatures where pure water would lock up. Chemistry on the surface looks rich but weathered. Ice is marked by sulfur and carbon compounds, iron and magnesium hinted at in grain and hue, dark organics baked thin by radiation. Callisto receives little tidal kneading, so its energy budget is modest. That makes it a conservative bet for life, perhaps not a fertile fermenter, but not disqualified either. In a universe where niches are often made of just enough, even a cold, salty sea can't be dismissed. Europa holds the bright lantern for now. It's only a touch smaller than our moon, with a surface temperature that would split steel with brittleness. But under that smooth, bright shell, the evidence lines up like careful stones. The ice is likely 10 to 30 kilometers thick. Below it, an ocean, perhaps 60 to 100 kilometers deep, moves under the pull of Jupiter. The moon is tidally locked, always showing one face, but it nods and flexes just enough to keep its interior stirred. That flexing warms the deep, the way kneading warms dough. Cracked patterns and chaotic terrains tell of rafts of ice that have drifted and refrozen. Magnetic signatures imply a conducting, salty sea. The surface shows long streaks where material may have risen from below and refroze as rust-red lines. Hubble has even caught what look like thin curtains of vapor arcing 200 kilometers into space. Most often, when Europa is farthest from Jupiter, plumes that might be the lids of local lakes breathing, or straws through which the ocean itself exhales from time to time. A tender trick of impact has helped with taste tests. When something large punches through Europa's crust, water from below surges up and freezes in the crater's floor. Reading those frozen pools reveals a brew that includes magnesium and sulfur compounds, hydrogen peroxide, and oxidants strong enough to feed certain metabolisms. Radiation at the surface breaks water and builds oxygen. Fractures and slow convection could ferry those oxidants downward. It is not fantasy to say that Europa's ocean might carry enough dissolved oxygen to support simple aerobic life, at least locally. Energy could flow from black smokers on the seafloor, hydrothermal vents that feed on the tension between water and warm rock, while chemical disequilibria, a fancy way to say food for electrons, provide a menu for microbes. On Earth, bacteria and even tough little animals like tardigrades pull off acts of survival in darkness, pressure, and cold, transposed into Europa's key. That song has familiar notes. Io, for completeness, burns rather than breathes, so close to Jupiter that tides need it to a fever, resurfacing it with sulfurous lava again and again. It is a laboratory for geology, maybe not for biology. but the heat it sheds and the tug it adds to the whole Jovian system are part of the reason Europa's sea stays awake. The tools we've used to learn this much have been mostly passers-by. Galileo orbited Jupiter in the 1,990 seconds and rewrote the syllabus. Juno, arriving decades later, has been tracing the planet's deep winds and peeking at the moons in flybys, catching Ganymede's magnetic sigh and Europa's cracked glass in high relief, even skating close to Io's hellish fountains. The next conversations will be longer. Europe's JUICE mission is already en route, tuned to Ganymede, Europa, and Callisto, with plans to settle into orbit around the largest moon after many tours. NASA's Europa Clipper is following a trajectory toward dozens of close passes, each one a sip of data, ice thickness by radar, chemistry by spectrometers, heat by infrared glow. Surfaces mapped in exquisite, calm detail. The idea is not to guess from afar, but to measure the way a doctor listens with a stethoscope, gently, repeatedly, from many angles. Habitability is a concept, not a guarantee. Water is necessary, but not sufficient. Energy is crucial, but must be accessible. Chemistry needs time and containers. The ice shells provide lids, the tides provide stoves, the rocks provide pantry shelves. Radiation near Jupiter is fierce at the surface, which is fine life, if present, would choose depth. The key word is disequilibrium, a river of available reactions that living systems can exploit faster than the inanimate world would. On Europa, oxidants from above could meet reductants from below. On Ganymede, layered oceans might set up a staircase of gradients. On Callisto, brines could remain stable for eons, cold and slow but continuous. None of this demands complexity. Single cells would be triumph enough, little bags of metabolism, drifting or clinging under aurora-lit ice. There is patience built into these seas. Sunlight barely reaches them. Seasons are more about orbits than weather. Storms are tides you cannot see. If we ever borrow a cup from Europa's ocean, the sample may look clear and empty, and yet teem in ways only a microscope can make obvious. If we never drill, plumes might carry whispers up to instruments that hover or sweep past, molecules caught and identified in the briefest of meetings. Even a null result, no organics, no biomarkers, only salt and silence would be an answer worth the trip. It would tell us something about thresholds, where chemistry stalls, where energy pools without consequence, where time alone is not enough. In the meantime, the moons keep their rhythms. Ganymede turns inside its magnetic shell, a planet in miniature, practicing sovereignty. Callisto rolls on, old and crater-rich, with an ocean that seldom betrays itself. Europa flexes, groans, remakes its ice, and tucks its sea tighter. Jupiter oversees with storms the size of continents, indifferent and instructive. The belt behind us continues to sift its dust into a pale wedge before dawn. Everything is connected by gravity and by the slow trading of light. Somewhere under kilometers of ice, a tide lifts and sets. Minerals dissolve and precipitate. Tiny gradients build and fade. The deep water remembers the pull of a planet it never sees. In that steady darkness, possibility does not shout. It hums. The hum of hidden oceans follows us outward, turning from salt and pressure into ice and light. Around Saturn, another kind of sea spreads wide, a braided surf of crystals and dust, barely there and yet bright enough to to draw the eye from a backyard scope. The old story says a mid-sized icy moon wandered too close a geological heartbeat ago and tides unstitched it, pouring its body into a ring of snow. Some versions give that lost world a name Phoebe or something Phoebe-like. Other studies imagine a doomed chrysalis moon. The dates cluster in the same neighborhood of time, tens to a few hundreds of millions of years. However, the tale is cast, a close pass, a pull beyond endurance, and then a long drift into lace. Even now, after centuries of watching, the rings keep their privacy. What we call the rings is a broad, translucent plane of material extending roughly 280,000 kilometers in radial width, where they are most obvious. But the structure's ghostly outskirts, tenuous arcs and veils reach far beyond, too diffuse for easy seeing. For all that's spread, the mass is modest on planetary scales, a mere sliver compared to a moon. Only a few % of the volume is solid. The rest is the hush between particles. Sunlight does the embroidery, turning ice grains into mirrors so efficient that, from certain angles, the rings outshine the planet they encircle. Up close, order appears. The broad bands we label D, C, B, A are themselves woven from many narrower strands, with clean gaps between them, absence sculpted by gravity. Saturn's own pull sets the baseline. The tugs of attendant moons add syncopation. At certain resonances, the rhythm snaps material from an orbit and clears a lane. The famous Cassini division reads like a pause in a poem. The innermost visible band, the wispy D-ring, seems to feather inward toward atmosphere, its tiny grains of water ice and methane frost fading into air. Outside it, the C-ring glows more surely, its particles small on average, a rain of meter-scale stones. Beyond that, the B-ring stands as the brightest wall, dense, optically thick, but only 5 to 10 meters deep through most of its body, with an outer edge that rises into a corrugated rim, the sculptural result of collective gravity and resonance. Farther out, the A-ring begins near 60,000+ kilometers above Saturn's cloud tops and runs outward some 15,000 more. Inside its dark lanes live shepherds. Pan cruises the Encke Gap, Daphnis threads the Keeler Gap, their gravity teasing waves and scallops along the edges like wind on tall grass. Beyond the main show lie the delicate F and G rings, braids and wisps, vulnerable to every nudge, and far afield, the vast E-ring, a gauze that reaches nearly to the orbit of the moon that feeds it. That moon is Enceladus, small enough to fit under the span of a big terrestrial county, and yet loud in what it says. The surface temperature sits near 75 Kelvin night absolute, and the air above it is hardly air at all. But along the South Pole, fractures nicknamed tiger stripes vent plumes of vapor and ice grains into space. Gravity is weak. Much of what flies leaves forever. Some of it becomes the E-ring's substance. The rest rains back as snow. Instruments have tasted salts, silica, ammonia, and complex organics in those jets, a chemistry box that implies liquid water in contact with warm rock. Models sketch a globe-spanning ocean beneath the shell whose thickness varies, thinner at the south, thicker elsewhere, kept from freezing by tides and spiked with antifreeze compounds. If life has favorite verbs dissolve, mix, react, Enceladus can conjugate them in the dark. Tidal timing matters here. As Enceladus moves along its orbit, Saturn's pull flexes the ice, opening and closing cracks. Plume activity waxes and wanes with that heartbeat. The ocean itself likely ranges from sub-zero at the roof to near melting at the sea floor, where warm rock could seed hydrothermal vents. On Earth, such vents feed ecosystems that live by chemistry instead of sunlight. It is not naive to imagine similar economies under ice, microbes trading electrons in warm, mineral-rich fluids, building a slow, patient ecology. A little farther out circles Tethys, larger and paler, a moon made mostly of water ice with a dusting of rock. Its surface wears two grand signatures. Odysseus, a crater almost half a world wide, dips 3 kilometers at its center. The scale feels comic until you remember the gravity is gentle and ice is stone here. Running a third of the way around the equator, Ithaca Chasma splits the crust a canyon up to 100 kilometers wide and several kilometers deep. One story says the chasm opened when a buried ocean froze and swelled, cracking its lid. Another ties it to the shock that excavated Odysseus, fractures racing around the globe and meeting themselves on the far side. Both tales share the same theme. Ice behaves like rock when it is cold enough, and rock behaves like memory when struck hard. Keep outward and the scene changes again. Titan steps into view wearing weather, larger than Mercury and wrapped in an atmosphere thicker than Earth's. It is the only moon we know with rain that reaches the ground. Not water, methane and ethane cycling from lakes to clouds to lakes again in a slow, amber monsoon. The air is mostly nitrogen. Sunlight and charged particles cook the methane into complex organics that clump and fall like brown snow. Under the smog, radar and infrared eyes have mapped shorelines and dunes, river deltas, and empty seas, waiting for the season to turn. Temperatures near 94 Kelvin make ice behave like granite. Where lowlands sag, black lakes gather. Where uplands stand, ridges rise from a crust likely stiffened by methane hydrates. Deep below, models place a salty ocean, perhaps laced with ammonia. Above a rocky core, 3,000+ kilometers across, atmosphere escapes molecule by molecule, but interior chemistry pays into the account, and the balance changes slowly enough to measure in eons. Titan invites long thoughts. In deep future sunlight, when our star swells and warms the outer system, haze could burn off, surface ices could soften, and different chemistries could wake. That is a far calendar. For now, the interest is nearer term, the way organic complexity piles up without life to organize it, the way liquid finds paths even where cold tries to forbid it, the way a nitrogen sky can wear rain and wind and carve landscapes of a kind we have not walked. Saturn's rings and moons are not separate scenes. They talk across space with gravity and grain. Shepherd moons sculpt ring edges and wear ring dust like makeup. Enceladus feeds the E-ring and is fed, in turn, by material falling back. Micrometeoroids darken bright ices. Electric charges loft fine grains. Resonances, those rhythmic tugs at simple orbital ratios, write ripples into ice and tilt waves into shadow. Everything is in conversation, and the conversation leaves marks we can read from 1 billion kilometers away. Numbers are the quiet part of that reading. Distances in tens of thousands of kilometers. Temperatures near absolute zero. Pressures so low that a sneeze would remake the local weather. And yet from such inhospitable arithmetic, gentleness persists. The B-ring's outer rim stands in sun like a low cliff of glitter. The A-ring's gaps breathe as Pan and Daphnis pass, throwing scalloped wakes that travel like whispers. The F-ring frays and reweaves, a thin braid caught between shepherds that tease it into knots and then smooth them. Even the vast, faint E-ring built grain by grain from Enceladus's exhalations reminds you that a moon the size of a small country can change the appearance of a giant's entire sky. Behind the spectacle, habitability keeps its own ledger. Enceladus checks boxes none of us expected a generation ago. Liquid water, energy gradients, organic inventory, a proven sample line to space. Titan adds a different promise: prebiotic chemistry at planetary scale, solvent cycles in the cold, questions about life's plasticity. Tethys and many of the others contribute context: how ice remembers heat, how impacts reshape worlds with low gravity and deep cold, how fractures tell you what a moon has tried to be. Sleep likes constellations of meaning, not lists. Picture it this way: Europa hums under glass, Enceladus whispers through jets, Titan dreams in hydrocarbons and rain. The rings themselves are snowfall caught mid-flight, suspended around a planet that sings in radio and storms. Across all of it, tides do what tides always do: transfer energy, keep water restless, keep crusts alive to motion. The same physics that folds an ocean into Europa's dark also combs a million snowy particles into Saturn's luminous scarf. Night gathers, and the giant at the edge of your imagination turns once more. Bands and storms rotate. A shepherd moon casts a thin thread of shadow across a bright lane. Geysers fountain into space and fall as a wider frost. Nothing asks to be hurried. The system breathes on scales too slow for the pulse in a wrist, yet just right for the quiet mind. Somewhere, a salt crystal forms in Enceladus's sea. Somewhere else, sunlight hits an ice grain in the A-ring and flashes a signal that began before you closed your eyes. The music holds, low and even, like tide under ice. That low, tidal music carries us still farther out, past the bright scarves of Saturn and into the dim, slow country beyond, where the sun is a small coin and worlds move like thoughts you have only once each season. Out here, near 40 astronomical units from home, a small globe circles on an elongated path. Pluto, faint as ash, steady as a heartbeat measured in centuries. Its here takes about 248 Earth years. In 1989, it brushed close at perihelion, just under 30 AU. And now, it is gliding outward again toward a far aphelion near 49 AU. It will not reach until the year 21 and 13. By size, it is modest radius, about 1,188 kilometers. Mass, roughly 1/8 that of our moon, and yet it holds a complicated interior and a weather of frost and haze that make it feel more like a story than a number. In 2006, it took its present title, Dwarf Planet, joining other distant kin like Orcus and Sedna that trace long, cold ellipses in the Kuiper Belt. From Earth, even the Hubble's sharp eye shows Pluto as a soft brown disk without much relief. For a true portrait, we needed a traveler. New Horizons left in 2006, coasted for 9.5 years, and by July 2015 swept past for a single, exquisite set of looks, hundreds of observations, gigabytes of data, a quick embrace that still unfolds in the hands of patient readers. The probe did not break into orbit. It glanced, gathered, and moved on, carrying the momentum of a long itinerary into deeper dark. Beneath the frost, Models sketch an interior layered like a quiet chord, a rocky, water-ice-rich core on the order of 1,700 kilometers across, wrapped in an ice mantle perhaps 300 kilometers thick, topped by a crust of volatile ices, nitrogen mostly, with methane and carbon monoxide. Heat from radioactive decay, held and focused by pressure, may keep pockets within the mantle warm enough to melt, and some versions of Pluto's autobiography include a deep, briny ocean, salted with ammonia, a bitterness that lowers the freezing point and keeps water liquid in a place where the average surface temperature rests near 60 Kelvin. On the face of this cold world is a mark you can recognize from a postcard, a pale heart called Tombeau Regio, centered near the equator and sprawling over a quarter of the globe. The western lobe is Sputnik Planitia, a smooth, bright plain about 1,500 kilometers across, depressed below the mean radius and paved with nitrogen, ice mixed with carbon monoxide and methane. In sunlight, those ices glitter. Some patches reflect almost 9/10 of the light that finds them. Few craters interrupt the plain, a sign of youth by planetary standards. The favorite origin story is dramatic. An impact in the last 100 million years excavated a basin that later filled, perhaps even with upwelled material, from a subsurface ocean that froze into a level floor. Across that floor, New Horizons imaged subtle polygonal cells 20 to 30 kilometers wide, a pattern like the top of a simmering custard, interpreted as convection, warm ice rising, cool ice sinking, the whole plain migrating in slow motion over geologic time. It is a gentle way for a frozen world to keep a kind of weather. Along the western rim, knuckled ranges stand up from the plain, Hilary Montes rising to roughly 3.2 kilometers, and in the south, Tenzing Montes climbs higher still, 6 kilometers or more, peaks made chiefly of water ice that, in this cold, behaves like rock. Not far away, a deep basin mantled with hummocky ice looks, to some eyes, like the vent and shield of an ancient cryovolcano. Not fire, but slush, not basalt, but ammonia water brine, erupting and freezing into drifts that keep the record of a world still able to move its own skin. Eastward across the heart, the surface darkens and roughens. Craters crowd the terrain. Along the equator, a procession of dusky patches, maculae marches like a string of beads, nicknamed the Brass Knuckles, and named more formally for deities and spirits from many cultures. The largest, Cthulhu Macula, spans nearly 3,000 kilometers and reflects only about 30% of the incident light. A low albedo mantle, likely built from Tholin's complex organic gunk, baked out of nitrogen and methane by solar ultraviolet and cosmic rays over long spans. The contrast with bright Sputnik Planitia is a relief map of time itself, fresh ice beside ancient varnish. Turn north and the tint shifts again. Lowell Regio wraps the polar latitudes in layered swaths, and in the present season of Pluto's long year, it is unusually well lit. The dwarf planet's axial tilt is large, and as the pole leans toward the sun, volatile ices sublime from lower latitudes and migrate toward colder traps, thickening thin air and painting the surface with bright snowfall. Seasonal change here does not mean blossoms. It means nitrogen haze in the sky and dunes of methane frost building grain by grain. Pluto does not spin alone. It dances with a partner so consequential that their mutual center of mass lies outside Pluto's body. Charon, about half Pluto's diameter and more than a tenth its mass, holds Pluto's face and shows its own, both worlds tidally locked to one another. Around them flock smaller, irregular moons, Nix and Hydra, found in 2005, Kerberos and Styx, added later, each only tens of kilometers across, likely captured or born in the aftermath of an ancient giant impact that may also have created the Pluto-Charon binary. New Horizons glimpsed them in passing, too brief for portraits with wrinkles, long enough to say hello. Charon's visible hemisphere, by contrast, yielded a few pages. South of the equator spreads Vulcan Planum, a comparatively smooth expanse of resurfaced ground, while to its north lies Oz Terra, older, cratered, and set apart by a system of great scarps and fractures that could girdle the moon. Near the boundary stands Kubrick Mons, a broad dome, 40 kilometers wide and several kilometers tall, with a moat-like depression encircling it geometry that invites the cryovolcanic explanation. A plug that rose from below and sagged after its chamber drained. Farther north, the pole wears a dark cap called Mordor Macula, likely tholin-rich frost, made from volatiles that wandered from Pluto's atmosphere and were cold-trapped by Charon's winter. Ultraviolet light and charged particles then cooked those volatiles into complex reddish organics that deepen with time. Some of Charon's wounds are grand. Serenity Chasma runs for hundreds of kilometers, tens of kilometers wide, and in places descends as much as 7 kilometers below surrounding terrain. Steep, shadowed walls make its depth hard to sound precisely, but the magnitude suggests global stresses, perhaps a subsurface ocean that froze and expanded, stretching the crust until it split. If Pluto keeps a briny sea today, Charon likely left its own long ago in a violence of ice. Back on Pluto, other chasms cut the ground in smaller arcs and radiating seams. The skin there is not static, even if its motions take eons to show. In every direction, the chemistry is whispering the same surprise. A world this cold should have gone still, and yet parts of it have not. Geology, it seems, can be measured by patience alone. New Horizons has long since left these companions, now coasting beyond 50 AU on a trajectory that will turn it, with time, into one more careful mote among the interstellar wind. Its transmitter will sing until its power runs low late in this decade by our calendars, and then a useful quiet will replace that voice. The images and spectra it sent will keep working after the instrument sleeps. Pluto, Charon, and their small retinue will keep circling a sun dim as an ember, trading light and frost and shadow in cycles the body can't feel, but the mind can learn to hear. Think of that heart-shaped plain slowly overturning, of mountains of water ice standing in air you could not breathe, of dark caps and bright snows, migrating with seasons that last longer than the written history of our species. Think of a binary world system turning around a point in empty space, the way two dancers turn around a held look. The outer solar system is often described as lonely. What it offers, when approached gently, feels more like reserve depth held close, secrets given on the timescale of drift. Beyond Pluto's pale heart, the dark does not empty, it widens. Out there, alongside the slow arcs of icy dwarf worlds, our own small emissaries keep moving tiny, warm-blooded machines unfolding a different kind of map. They are not planets, not even pebbles by cosmic standards, but they carry our questions farther than breath can go, and their paths stitch the outer quiet to everything we have learned closer in. One of them, New Horizons, left home in 2006 with a straight, serious purpose: reach Pluto and its companion. Look closely, keep going. It borrowed speed from Jupiter, swung past the great planet in a brief waltz that yielded crisp views of cloud bands and moons, even a fleeting record of Io's volcanoes flinging fire into space. Then the long coast to the Kuiper Belt, the quick, meticulous encounter in mid-2015, and the flood of images that turned a smudged dot into valleys and nitrogen snows and a plane that circulates like a sleeping lung. When the work at Pluto and Charon was done, the craft did not stop. It threaded deeper among the slow, dark neighbors, paying a close visit to Arrokoth and catching glimpses of others by careful aim. Its heartbeat comes from a radioisotope generator, a tidy ember that cools a little every year. Instruments will wink out one by one across the later 2020 seconds and into the next decade. Long before the last whisper fades, New Horizons will have slipped beyond 100 astronomical units, another speck riding the sun's faint wind toward the interstellar night. This is a pattern we already know. Two older travelers, Pioneer 10 and Pioneer 11, were the first to try the door. Launched in the 1,970 seconds, each crossed the orbits of the giants, learned the scent of Jupiter's radiation belts, and returned images that made the planet's storms and moons feel proximate and alive. They measured magnetism and heat and taught us that Jupiter glows with more energy than it receives from the Sunday. Pioneer 11 went on to feel Saturn's field and see its ring plane, and the shy faces of Mimas and Titan in grainy, brave detail. Their power, too, was finite. Their antennas fell silent, one in the mid-1,990 seconds, the other early in the new century. Somewhere beyond the reach of our receivers, they continue outward, keeping a human plaque for company. Two figures, a map of pulsars, the simplest of greetings etched in gold. The Voyagers followed and broadened the scale of what possible could mean. Voyager 2 took the grand tour Jupiter, Saturn, Uranus, Neptune, cataloging new moons, revealing ring systems where none had been suspected, sketching atmospheres with eyes tuned to many colors. Voyager 1 focused on speed and depth, Jupiter and Saturn, then a hard turn above the ecliptic and out through the sun's fading influence into the local interstellar medium, where charged particles and magnetic fields carry a different grammar. Both spacecraft have crossed the heliopause, that shifting border where solar wind yields to the thin pressure of the galaxy. Their instruments, husbanded carefully, still take a few key measurements. Their radios still send back counts and murmurs, spaced by hours of light travel time. Gold records rotate slowly on their sides, full of songs and greetings and directions, meant for no one in particular and anyone at all. Time bends around them. In a few centuries by our clocks, Voyager 1 will reach the inner guessing line of the Oort Cloud, the comet reservoir that may blur the solar system's true edge. Tens of thousands of years later, it will drift clear. Much later still, it will pass within a couple of light years of a dim star and keep going, unremarked. Voyager 2 has its own appointments, another red dwarf in another constellation, a long brush past the wider neighborhood. None of this requires our watching. The trajectories are promises the probes can keep on their own. Between these named journeys lies the broader, humbler truth. We have only just begun. Spacecraft fade. Curiosity does not. The first signals that reached past 50 astronomical units were milestones, not because they crossed a finish line, but because they demonstrated a kind of patience, years of steady flight for minutes of revelation, long silences between messages that rearrange the furniture of our understanding when they arrive. Gravity assists, carefully planned sleep modes, instruments tuned to sip photons and ions instead of gulping them. The craft are clever extensions of the same craft in us. Think of the map that has been sketched by this flotilla: Jupiter's excess heat, Io's fountains, Saturn's rings as a living weave, Uranus's sideways spin, and Neptune's dark, fast storms, Triton's nitrogen plumes, Pluto's convection cells and water ice peaks, Erekoth's contact binary, two bodies joined like a slow embrace. Each entry adds mass to the sense that the solar system is not a tidy model set on a classroom shelf, but a weather, an ongoing set of processes that take eons to say what they mean. The far edge is not a border, it is a gradient, a thinning of one wind into another. The likely futures for our machines divide like paths in a quiet wood. Perhaps, one day, descendants with surer hands and longer views will go out and catch them, frame them in museums like dragonflies caught at summer's end. Perhaps they will crumble into their elements, a slow sandblasting by dust and radiation, until only trajectories remain. Perhaps a careful accident will end a journey abruptly against a small, dark object no one ever named. None of these endings diminishes the fact that, for a while, we could build something that knew how to leave and then did. Meanwhile, the galaxy waits without impatience. Hundreds of billions of stars in one spiral, each with its own local weather, many with families of planets, some with seas, some with storms, some with only stone and night. Trillions of worlds, in totals too large to hold in speech. We are not tasked with counting them all. We are invited to take the next step and then the next. The room is quiet now. The mind can do its own coasting. Imagine a probe turning slowly as it sleeps, thermals balancing, a tiny heater keeping an instrument warm enough to work. Imagine a bit stream leaving an antenna, a thread of information stretching across cold like a spider line, moving at light speed and still arriving days later. Imagine the sun reduced to a bright star behind the shoulder, then to a star among stars, unremarkable and necessary. If you listen for it, there is a sound to all this, a steady carrier wave, faint but certain, saying only, still here, still going, still sending what I can. This is a good place to pause. The map we've traced from the sun's fire to Pluto's frost and out into interstellar dusk is not complete, and that incompleteness is its comfort. Somewhere, a new instrument is being assembled under bright lamps. Somewhere else, a young observer is learning the sky by heart. The cosmos will keep its patient tempo. Our part is to keep time with it, eyes open when the data arrives, hands restful when it does not, and to let the vastness do what it does best, turn mystery into a place you can stand. Close your eyes when you're ready. The journey will continue whether we're watching or asleep, and when we wake, there will be more to read in the dark.